And then the cat then collapses into a dead cat or a live cat. Well, that means that observation determined existence. So you're now left with a very horrible, absolutely incredible paradox. Either the act of observation determines the existence of a cat, or the cat is simultaneously dead and alive. Both alternatives are mind-blowing. Both alternatives shake philosophy to the very core. Let's take the first alternative. Observation determines existence. But observation requires consciousness. Therefore, consciousness makes an observation, and then we see the cat is alive. Well, I determine the fact the cat is alive. Well, who determines me? Somebody has to look at me to determine that I'm alive and I'm not dead. Well, who determines him? Somebody has to look at him. And this is called Wigner's friend. Wigner was the winner of the Nobel Prize. He helped to build the atomic bomb. And this is called Wigner's friend. I have an infinite sequence of Wigner's friend. So who's the ultimate Wigner's friend? God. So starting with quantum theory, which is the most objective reductionist theory of all time, you go all the way up to God. Now let's say you don't want that. Let's say you don't believe in this Nobel Prize winner. Let's say you believe in the other theory. The other theory is even worse. The other theory is many worlds. Most Nobel laureates now are leaning toward the second. Steve Weinberg, winner of the Nobel Prize, has said the following. Imagine you're in a room and many radio frequencies are in the same room. Your radio is turned into one frequency, but you're very comfortable being in a room with many frequencies, right? But you tune into one. Well, these frequencies are now wave functions. In this room, there's the wave function of dinosaurs. In this room, because they never died 65 billion years ago, because a cosmic event prevented the extinction of the dinosaurs. In this room, there's the wave function of aliens, because perhaps aliens decided to colonize the Earth millions of years ago. In this room, there's the wave function of Alexander the Great. Perhaps he came all the way to the Americas instead of being just conquering most of the old world. Think about it. Your mind goes crazy. This is the multiverse. So welcome to the multiverse.
I'm going to explain to you what's known as the central mystery of quantum mechanics. Richard Feynman, the American physicist, said, this is the central mystery of quantum mechanics. There's lots of weird stuff that goes on in the quantum world. Hit you with this, and it basically tells you what it's all about. It's called the two-slit experiment. I'll start with this. Imagine you have a source of light shining against a screen with two slits. Now, for the pedants in the audience, this source of light has to be monochromatic light, light of a particular wavelength, whereas, of course, a light bulb is white light, and that's made up of all the colors of the spectrum, lots of different wavelengths. But imagine this is just a single wavelength of light, and you can see the light is coming out in waves like ripples in a pond. That's the nature of wave-like behavior. As the light hits the screen, it squeezes through the two slits, and each slit in turn on the other side becomes almost like a new source of light, and the light spreads out, it diffracts. And as the waves of light overlap, they will interfere with each other. So where a crest hits a trough, they will cancel. Where a crest hits a crest, they will amplify, and so on. And so on the back screen, you end up with what's called an interference pattern, a series of light and dark fringes, where the waves have either cancelled out or worked together in phase. That's fine. That's not quantum mechanics. That's a property of light that goes back over 200 years that we've known about since the early 19th century. Imagine doing the same experiment again, but doing it not with waves, but with particles. Do it with grains of sand. So this is the same experiment, but I've tipped it 90 degrees. Rather than waves that are spread out that wash up against the two slits and squeeze through, here you've got individual particles of sand, and each particle will either go through one slit or the other. And so you see they will sort of drain through, and you get two bumps underneath each of the slits. So the two peaks is reminiscent of particle-like behavior, whereas the multiple pattern of interference is wave-like behavior. What if we do the same experiment with atoms? Well, so imagine we have an atom gun, something that can fire atoms, a stream of atoms. You can't see them because they're very small. Let's block off one of the two slits. So these two slits are the dimensions and separation of the slits is chosen appropriately to show us how atoms do things. And so far so good, nothing strange here. You'll see a lot of atoms hitting the back screen. So this will now have to be some sort of photosensitive screen whereby when an atom hits it, it'll give off a little flash of light to say the atom has arrived here. So the atoms are arriving as these little pinpricks of light that we see. Of course, a lot of the atoms will be blocked by the first screen. They won't go through that slit. But those that do get through to the other side, and you can see there's a bit of spreading of the atoms. But if we didn't know anything about atoms, you'd say, well, that's fine, we can understand that. A lot of the atoms are going clean through the slit. Some are sort of maybe bouncing off the edge of the slit, and so they're sort of being deflected a bit, which is why you get a bit of a spread. The first mystery of quantum mechanics comes when we open the second slit. Because now we see something that's very much like the interference pattern we got with light. Rather than having two bands of spots where the atoms have gone through the two slits, it's as though the atoms have gone through the slits behaving like waves, and you get interference of the waves and you get these bands. If we know nothing about atoms or quantum mechanics, you could try and rationalize it and say, well, maybe atoms behave in a very strange way, and only a certain number of them are allowed to all sit together. And so, me and my gang, we're all going to go on this slit. No, sorry, no room for you. You go to the next slit above. And by the way, there's this rule that no one can go between the two bands, but a few naughty atoms do. So there's a bit of a scatter. We don't. There could be some forces between atoms that make them coordinate their actions in a way to give this pattern. That's not mysterious. That's just, we just don't know how atoms do things. But we can be clever, and we can force the issue. What if we were to not send the atoms all through at once, but send them through one at a time? Leave enough of a gap for the atom to get through to hit the screen. Of course, as I say, some atoms will hit the first screen and not get through, but those that get through will hit the back screen. So let's run the experiment again slowly, and gradually you'll see as the atoms go through, they'll look like they're just randomly arriving on the other side. You keep sending atoms through one at a time, and gradually that same pattern appears. So each atom by itself is somehow contributing its small part to the overall wave-like behavior that we see in the interference pattern. How does it do it? How does, we know the atom's a tiny localized particle, we can't see it, it's too small to even see under a microscope, we're firing it at the screen with the two slits. Some moment later you see a flash of light on the back screen. It's arrived in a localized point, it's not spread itself out. You don't get sort of like a wash of a faint light across the whole screen. It's a little point. The atom is localized, it's arrived in a certain location. And yet, it somehow seems to have been aware of there being two slits, not one, because it's given rise to this interference pattern. How does one atom do that? Does it split in half? Does it become like a cloud that goes through both? Well, we can try and be even cleverer. What if we were to spy on the atom and see where it goes? We can gently just observe which slit it goes through. So you put a detector just above the upper slit that will flash or beep whenever it sees an atom go through that top slit. Sure enough, you fire the atoms through, one at a time. 50% of the time, the detector will beep. The other 50% of the time it doesn't, the assumption being that the atom has gone through the lower slit. But of course, I've been cheeky here. I haven't shown you the results of the experiment. That's what you get. 50% of the time, it beeps, and you see a spot arrive adjacent to the upper slit. The other half of the time, it doesn't beep, but you see a spot arrive at the lower slit. So, yeah, it's picked out the atoms that have gone through the upper slit, and not the ones that have gone through. So each atom does go through one slit or the other. But that's a different result to what we had earlier. So here's the last bit of sneakiness that we can play with atoms. Surely now, we're going to get to grips with it. Leave the detector there, but just very quietly go and unplug it. Don't let the atoms know that you're not spying on them. Make them think that you're still detecting them. So, yeah, okay, we're going to run the experiment, atoms, okay, get ready, one at a time, we're going to be checking on you. All right, so run the experiment again. Now, if you can explain this using common sense and logic, do let me know, because there's a Nobel Prize for you.
This is a double slit experiment. It's a very famous experiment. This experiment has probably been done more times, more places, by more people than any other single experiment in the history of science. And it's because it gives such strange results that everybody wants to do it and see if it works like that for them. So this has been replicated over and over and over again, and whenever done properly, it always gives the same results. It tells us something very important about the nature of reality. Here's what happened, and I'll show you why it's such a famous experiment. Early on, we knew that waves, if you had a wave came to this thing, we have a barrier, a hole, a barrier, and a hole. It's called a slit. And it's two of them. There's a double slit. That's where the experiment comes from. That if a wave came here, some of the wave would go through this slit, some of the wave would go through that slit, and the distance from here to here is a little shorter than it is from here to here, right? We can see that. That's pretty obvious. If that difference in distance turns out to be like this, so the wave coming from the top hole and the bottom hole are shifted in distance one whole wavelength, then they both dip at the same time, they both crest at the same time, and you get a spot of light there. But if they happen to be just that difference in distance, where one gets to a peak just as the other one gets to a hump, you add them together, you get nothing. That's why you get nothing there. So what happens is you get this series of spots. It's called a diffraction pattern when you have waves going through the two slits. So they did this experiment with the double slit. They found a way to just fire one photon at a time at the slits, a particle. What they expected to see was this. What they saw was a diffraction pattern. Okay, now that was a surprise. They didn't expect that, so they said, well, there's something funny going on here at these slits. So these little red things are detectors. And they said, we're going to put detectors there at these slits, and we're going to see what's going on. And they did. They detected every time a photon went through this slit, the detectors would say, no, it went through the upper slit, or the detectors would say it went through the bottom slit. And whenever they did that, they got this pattern. So now the problem was, we take the detectors away, and you get this pattern. Then the idea with those detectors, they're doing something there. But they found out, and these are called quantum eraser experiments, they found out that you could take this data with these detectors, take all the data, detectors are working, it tells you exactly what slit each one goes through, but you don't look at this data, and you don't look at that data yet, you just take it. Now if you look at it, you'll get this. But if you don't look at it, and then you erase this information of which slit they went through, you get this again. See? So obviously reality is not objective. That's the double slit experiment, and that's why this is such a big deal, because it shows that reality is not objective. There's something else going on here. That's what we want to talk about. Well, I will give you a little experiment that I'm going to make up. This is not an actual experiment, what I'm going to tell you. This is just a logical equivalent, so it's easy for you to follow and understand. Actual physics experiments are very complicated, and they're very hard to explain, but this is, like I say, a logical equivalent. Let's say that we take 102 of this experiment. In other words, we're going to measure what slit it goes through, and then we're going to keep track of what happens over here on the screen. And we're going to do that just 102 times. And we're going to take data for an hour, put that in the computer, take the data again for another hour, put that in. And what we'll do is the first one we'll take this data, put it in an envelope, call it detector data experiment 1, and we'll take this, put it in another envelope, call it measurement screen data experiment 1, put those two envelopes into a big envelope and call it experiment 1. You with me with that? So I got an envelope that says experiment 1, and I've got inside that I've got two envelopes. One of them says detector data for experiment 1, and the other one says measurement screen. So I've got all my data in here. So it's just an easy way for us to keep them straight. So we're going to do that 102 times, and because we're doing this experiment, we always expect that as the result. So after we have 102 of them, we look at the first one we did, and we take this data out of the envelope, take that data out of the envelope, and this is exactly what we see, just what we expected. That's the experiment we're doing. And then we take the last one we did, and we do the same thing. We want to make sure that they're the same, right, on both ends. So we do that, and we get exactly this. You know, we get the two spots of light here. Is what we get. So the first one and the last one are like that. We assume all the ones in the middle were like that because they were all just done together. All right, but now what this delayed quantum erasure means is that let's take the 100 envelopes that are left, right? We got rid of number 1, we got rid of, the first one and the last one. Now we have 100 left out of the 102. We'll take those 100 and we'll shuffle them, we'll randomize them up. Then we'll deal them out into two piles of 50. Now, one pile of 50, we will look at them. We'll take the envelopes out and look at them, and every one of them, all 50 of them, will look just like this. We have the two spots here. Now the other 50, we'll take out the detector data of each one of the 50, put them in a pile, and set fire to them. We're going to burn them. We're going to destroy them. That's our erasure experiment. Okay, I'm making a very simple concept in the erasure experiment. We just burn them and destroy them. And no, they're not still readable in the ashes. We'll take the ashes and put them in water or something. Don't complicate the experiment. We're just going to burn them. That's going to get rid of them, and they will be erased. And then we'll open up these envelopes, and every one of them will be a diffraction pattern. See? That's what I mean by a delayed quantum erasure experiment. Every one of them will be. And you're thinking, how could that happen? You see, the experiment was done, let's say, a year ago before we took these envelopes out and sorted them. It doesn't matter. 10 years ago. The amount of time is irrelevant. In these experiments, they're actually done like 10 nanoseconds. But it doesn't matter. If you can do it in arrears, you can do it any amount of time. So that's why this is weird science. It looks like, depending on what you do with this data, you make this change from this output to that output, right? That's what it looks like. But that's just because you believe you live in an objective reality. You see, in a statistical probability reality, this is still indeterminate. It hasn't happened yet because you haven't looked. You see, you don't know what it is. In an objective reality, you know because you did this experiment, that's what it had to be. So you believe that's the way it is, and then you somehow magically changed it to this. Well, there's no magic involved. It's just that because this data hasn't been looked at, it doesn't really exist yet in this reality because we live in a probabilistic reality. I know you're thinking, that sounds impossible, but that's because you are ingrained from your culture with the concept of an objective reality. You believe that's the way it is, so when you see this or hear about it, it just doesn't make sense.
At the moment of decision to observe, the waves became particles. And not only that, but they actually made a record of themselves as having traveled through the slits as particles. Deciding to run the observed experiment causes the waves to become particles, and this causal force extends backwards in time.
Our choice of what experiment to do determines the prior state of the electron.
Running the experiment unobserved does not cause this effect. When John Wheeler first proposed adding the delayed choice protocol to the double slit experiment, he asked us to imagine a distant star that emits a photon billions of years ago and sends it towards the Earth. However, on the way, it must pass a dense galaxy. Gravitational lensing will make the light bend around the galaxy. Billions of years later, upon reaching the Earth, an astronomer chooses to use a binocular-type detector and focuses half of it on the left side of the galaxy and half of it on the right side. How the astronomer chooses to measure means the photon could only have taken one path and would display a clump pattern. So how we choose to observe in the present determines how the photon behaved billions of years ago. It only makes sense if the universe is a simulation and all parts are equidistant in space-time with respect to the source of the simulation, like in a video game or a dream.